Okay, so I want to do one Faraday's Law practice problem from the book, and this is example or problem number 5 in chapter 29. A circular wire loop of radius of 12 centimeters is immersed in a uniform magnetic field of half a Tesla with its plane normal to the direction of the field. If the field magnitude decreases as a rate of 0.01 Teslas per second, at what rate should the radius of the loop increase so that the induced EMF within the loop is equal to 0? Okay, so let's first of all try to draw ourselves a picture of that so we understand what's being asked. You've got a magnetic field, and you've got, I messed up my focus. Hold on. There you go. Okay, you've got a magnetic field. Does it say whether it's into or out of the page? Doesn't matter, because we get to pick the directions. So let's say the magnetic field is coming out of the page. And the initial magnetic field is equal to, what was it, half a Tesla, right? 0.5 Tesla. But now it's going to decrease at a rate of minus 0.01 Teslas per second. 0.01 Tesla per second. And you've got a circular loop within this that has radius r. And as the magnetic field decreases, the flux through the loop is going to decrease, and that would generate an EMF in the loop. Let's figure out the direction that that would be, just for practice. I've drawn the magnetic field out of the page. If the field decreases, that's a decrease in this field out of the page and a decrease in the flux through the loop out of the page. You're going to fight that decrease by creating our own field in the upward direction, which means we're going to create a current around the loop this way. Okay, that would fight the decrease through the loop. But instead of that, what we're being asked is at what rate could we increase the radius of the loop such that it canceled out that change in flux? So we can actually calculate the EMF generated by this change and then calculate the corresponding EMF that would be generated by the change in R. But what we have to realize, what's a better thing to realize, is we want the rate of change of the flux to be equal to 0. Right? We want there to be no net change in flux, which means we just need to conspire to change the magnetic flux by exactly this amount. So how do we set this up? Let's see. So the magnetic flux is just B times the area. Right? We don't need to worry about the dot product. We don't need to worry about integrating B as constant, and it's perpendicular to A. So that's equal to B times pi r squared. If just B is changing, then the rate of change of the flux, d phi b dt, would be equal to dB dt times pi r squared. If r is changing, the rate of change of the magnetic flux, d phi b dt, is equal to, the rate of change of this is equal to 2b pi r dr dt, if r is changing. But they're both changing. Okay? So we need to be careful with how we tackle this, this derivative here. we could simply say this is equal to this, and that would give us the right answer. I want to be a little more careful though. If both B and R are changing, what you really do is write phi is equal to B times pi R squared. So the rate of change of that flux, d phi dt, is equal to, and then use the full-on product rule and chain rule to take the derivative of this whole thing, knowing that B is not constant and R is not constant. So that would look like this, dB dt times pi R squared plus 2B pi R dr dt. That's just taking the derivative of this with respect to R and using the chain rule. So it's B times pi times 2R times T dr dt. I just pulled the 2 out front. And that has to equal 0. Okay. What does that look like? The pi's cancel, one of the r's cancels. I've got dB dt times r squared is equal to minus 2b r dr dt. If we solve for dr dt, we get dr dt equals minus 1/2 r times dB dt. And I lost a b. I lost that b, so it's r over b dB dt. All right, check our algebra here. We solve for dr dt. I get a minus 1/2. I get a r squared over r, and I get a 1 over b. So minus 1/2 r over b dB dt. And those are all numbers that that we know in our problem. Dr dt is equal to minus 1/2. What was the initial radius? Did they give us the initial radius in the problem? Yeah, 12 centimeters. So 0.12 meters over the magnetic field is 0.5 Tesla times the rate of change of the magnetic field was minus 0.01 Teslas per second. Okay? And that's going to give us, the Teslas cancel, that's going to give us meters per second. So we can just pull out a calculator. 0.5 times 0.12 divided by 0.5 times 0.01. I get 1.2 times 10 to the minus 3 meters per second. 1.2 times 10 to the minus 3, so 0.0012 meters per second should be the rate of change of the circle, 1.2 millimeters per second, if you prefer. So if the circle increases r by 2 millimeters per second, that will offset the decrease in magnetic flux caused by the magnetic field decreasing. That was kind of a weird problem. Maybe we'll do one more before I turn you guys loose on the homework.